Anika, I think you can go ahead and get started.
Okay. All right, you can hear me right now, right?
Yeah.
Okay, great. Hi, everyone. Thank you so much for joining today. My name is Anika, and I'll be hosting this week's Gem Hunt. So Gem Hunts are programs launched by Girls Empowered by Math, a student-led organization dedicated to empowering girls to pursue their love for mathematics. We work extensively with STEM for Her, our sponsor, which is a nonprofit organization that has invested over $500,000 to engage more women in STEM. So this week, we'll be hearing from 5 different female professionals who extensively use math in their work. Yesterday, we heard from Dr. Von Cook, and today we'll be hearing from Dr. Groth. Over the week's course, you'll learn about the versatility of math and its vast potentials. And every day, we will listen and interact with a math-based presentation, after which we'll separate into breakout rooms to solve a challenge problem, and we'll join back as a group, realize the correct solutions, and complete our program. You will need your workbook, which you should have received yesterday. If not, just let us know. And I like to print it out, but if you want to work digitally, that's fine as well. Also, remember this is an interactive program, so participation is really important to fully benefit from this experience. And that leads us to our keys to success. So please follow basic Zoom etiquette. That includes not annotating on our screen, keeping your microphone muted while the presenter is speaking. And as mentioned, when breakout rooms are open, please discuss the problem with each other. They're challenge problems, so they require collaboration. And finally, please ask questions because this is a program to learn. Finally, if you weren't aware, Gem Hunt is offering a certificate of achievement if you attend all 5 days. If you miss one of the days, you can still earn the STEM for Her certificate program, but you'll have to write like paragraphs and stuff to obtain that. We strongly encourage you, though, to participate for the entire week. And that being said, let's begin. So I'll stop sharing now, and Dr. Groth, if you want to take the reins.
Okay, thank you very much. So welcome everyone. I'm Dr. Katrina Groth. I'm an assistant professor at the University of Maryland in the Mechanical Engineering Department. And I'm excited to be here today to talk to you about hydrogen quantitative risk assessment. So before I get started into the challenge problem, we can talk about me. So I'm an assistant professor, as I mentioned. So I've been teaching at the University of Maryland for 4 years now. And one of the things about life as a professor is that obviously I use a lot of math in engineering. And so my job it's about half teaching and half research. And so both of those things are really closely related in what I do. And there's really 3 things, like 3 research areas that I work on, and they all use the same kind of math. So I work on nuclear power plants, so trying to figure out how to make them safe, efficient, reliable. On the other side, I also work on hydrogen gas stations. So you have probably seen, regular cars. You've seen cars that use gasoline, cars that use diesel, cars that use batteries. Another type of renewable technologies is hydrogen gas stations or hydrogen cars. They would have gas stations, just like when you go to the normal gas station here for gasoline, but we don't have very many of them yet. So one of my big problem spaces has been figuring out how do we make hydrogen gas stations safety standards when they don't exist yet. And then I also use a lot of work on oil and gas pipelines. And again, all 3 of these areas have a lot of math involved in them, and they actually relate to each other really closely because they all involve mechanical systems, people, electrical systems, and really complicated physics and operating environments. So about that covers kind of what I do day to day. for fun. Professors are people too. I love to travel. I love my cat. You will possibly see my cat on this Zoom because it's almost her dinner time. So if she comes by, she always gets really excited about math as well. As you can tell, this is a picture of her with the textbook that I use in my class. And then also you see a picture of me eating ramen in Tokyo when I was there actually to visit some hydrogen gas stations. So I'm a professor by day, regular person by night. So why do people study risk and reliability? So you can actually get a degree in my field, which is reliability engineering. We're a little tiny piece of mechanical engineering. But what you'll find out is that everything in the US, our economy, our security, and our quality of life depends on these really complex engineering systems. So things like power plants, pipelines, aircraft, all kinds of things. So engineers build those. And it's a big part of engineering is creating those technologies. But one of the things you'll find out if you study engineering is that engineering doesn't stop when the airplane is finished. There's a lot of engineering that has to start when the mechanical system is finished and delivered. So when we look at things like safety and reliability, those are things that engineers have to do continuously. So we're not always building airplanes, we're actually figuring out how to make them safe and reliable under real world conditions. And one of the biggest things that we need in engineering is to figure out how to prevent and mitigate and recover from when things go wrong. Because when we don't do that effectively, you actually see the accidents. So what's interesting about the type of engineering I work on is that you never know what I do as long as I do it right. But until, when something goes horribly wrong, you'll recognize some of these famous accidents that have happened. So on the left, we have, this is the Deepwater Horizon explosion in the Gulf of Mexico. Photo number 2 is the Fukushima nuclear power plant. Photo number 3 is one of the Boeing the Boeing MAX aircraft. And on the right, we have the Challenger accident. So what we really try to do is prevent these accidents from happening before they happen, and also learn from what we did, learn from those accidents so we can prevent them better next time.
I have a quick question.
Okay.
So with the canal, I heard was it last month? I think where it got backed up. Would you guys work on that, and how would you mitigate that?
Yeah, that's a great question. So actually one of my students just started looking at that because that's another type of system where you had this mechanical thing, you had these people, you had this environmental system, all kind of interplaying. And so the same approaches that we're going to learn today are the way that I would start the problem. It's not something that I have a short answer to, because engineering is never as satisfying as, oh, let me do, one quick math equation and I'll give you the answer. But essentially what we would do is we would follow this risk assessment approach, and we would figure out first what are the things that could go wrong. And then we have ways of prioritizing which ones we actually implement based on probability mathematics. So someone would build a really large model, kind of like the one I'm going to show you today. And once we have that model, we would do more math with it to see which preventive actions are most likely to help us recover from a failure. So there's bad approaches to talking about failure. If it hasn't failed yet, that doesn't mean it's not going to fail. We also don't want to say, of course it's safe, I designed it. No engineer is going to work thinking we're going to make something that's not safe. So we have to really think about that safety throughout the life cycle. We have to think about it when we're building it. We have to think about, making sure that we know how to appropriately make it safe, because once something has happened, it's kind of too late. And if we bury our heads in the sand and ignore it, all we're doing is making it harder for us to come up with the right answer, rather than being kind of honest with ourselves. So it's a lot better to deal with safety long before anything happens. Like I said, the best day will be when you're like, I've never heard of her work. and that's a good thing. So we always want to think about, how we deal with safety, even if it hasn't, been a problem yet, because once it is a problem, it's really damaging to both the industry you're in, but also to the engineering profession. So that's where we get into what my field is, reliability engineering. So that's what we do. We figure out priorities, we encourage conversations among all the people that are involved, and we build a common basis for talking about safety. And so there's basically 3 questions we think about, and that kind of points to the answer I had. First, we have to figure out what the system is supposed to do. And so we learned that through our regular engineering curriculum. And then once you know enough about how the system works, you start thinking about, well, how do things go wrong? How do things fail? And then the last thing we do is we come up with those strategies to reduce failure. So maybe we redesign something, maybe we operate it differently. Maybe we put a second captain on our ship when we're entering the canal because that captain has navigational capabilities that we don't have. Maybe we do some more maintenance. Maybe we dig out the canal. There's a lot of different strategies to reduce failure, but you have to figure out which failures you're trying to reduce. And at this point, I always talk about this quote here, this old adage of a ship in the harbor is safe, but that's not what ships are built for. So we always have to remember that, of course, we want these systems to be safe, but if we try to make a perfectly safe airplane, it probably isn't going to fly. So we always have to remember that, that we have to make sure that we're addressing both the need to have these systems, but also the need to have them safe at the same time. So it can be more complicated than just trying to make the airplane fly, because we're trying to make the airplane fly, but not cause problems, but not, cause regulations that keep the airplane from being able to fly safely. So it's I think it's a really fun and fascinating part of engineering, but it's also a very challenging field. So that's pretty much what I do on a day-to-day basis. So then what I'm going to do is I'm going to shift to what the challenge problem is and give you the problem setup. So everyone should have the problem in their workbook, but I'm also in the next few slides, I'm going to give you some information in some of the slides that you might need in addition to what is in your workbook. So there's just 1 or 2 things. You might want to have your pencil handy. And if you see something, you might want to jot a couple of things down. So good news, I said I worked on hydrogen cars, and hydrogen cars are actually here. They do exist in the US. This is a picture of a hydrogen car that someone I know brought to the University of Maryland one day to show off. So you probably haven't seen them. Usually if you're at a hydrogen conference, they put really cool pictures on them. If you're just driving around DC, they just look like regular cars. You probably wouldn't know that you were standing next to a hydrogen car if you weren't super excited about hydrogen cars the way that most of the folks I work with are. So the hydrogen cars are here. They're more prevalent in California. They're run on fuel cells. They're really exciting because they're 0 emissions, just like battery vehicles. They're a type of electric vehicle. But the difference is, instead of plugging them in for 8 hours, you put fuel in them when you go to a hydrogen fueling station. So hydrogen is a renewable fuel. You can refill it really quickly. You're at the gas station for just a few minutes. We call it a fueling station, not a gas station, because it's not gasoline. Basically the same thing. You drive your car up, you put the nozzle in, and everything's great. So the cars exist, and Toyota, Hyundai, BMW, Mercedes, Chrysler, Daimler, they all have a hydrogen car that people can buy in some part of the world now. But the problem is there are not very many fueling stations. And you can't have cars if you don't have a place to refuel them. Okay, so sorry, I wanted to get this. So we want to build fueling stations. And when we want to build a fueling station, there's a lot of people that are involved in this. But one of the things we have to do is get a permit from our local fire authority or our local fire chief. And so when I was writing this problem, I was really excited when I was looking up the Prince George's County fire chief, and I found out that she is a woman. Her name is Tiffany Green. I do not know her, but I thought it was super cool that I ran into, in making this problem, another woman in engineering, obviously pioneering also because she is PG County's first female fire chief. So we'll use Tiffany Green as our example fire chief. So she wants to know, is your hydrogen fueling station as safe as a gas station? We have lots of gas stations in this county, but if you're going to put this hydrogen station in there, we have to figure out if it's the same level of safety. So how do we know? We have to give her some evidence. We can't just be like, oh, well, you know, BMW told me it was safe. She needs evidence, and that's her job, is to make sure that it meets the same standard. So one of the things she would normally do is go in and check the codes and standards. So there's not a universal criteria for what's safe. There's no rule that's like, okay, well, if you do exactly this, you're safe. It's not that easy. So what we do as engineers is we create these regulations, codes, and standards. And they help us determine what is safe enough for a certain country or a state or your county or your industry. So what is seen as safe here in the DC metro area is totally different than what's seen as safe in Tokyo, Japan, or what's seen as safe maybe even in rural Texas. So different jurisdictions have different standards. Dozens of experts develop these. They're updated every 3 years. So you end up having, just thousands of expert hours spent developing these codes. And one of the things that really helps develop them is risk assessment. So what is risk assessment? Well, risk is just the potential for a loss. So when we talk about risk, there's two things we're worried about. We know that we're going to lose something. There's no, risk is always something that has a potential bad outcome. And there's always potential, which means there's uncertainty. So there's those two elements. There's the uncertainty and the loss. So we never say, oh, there's a risk of winning the lottery, because that'd be great. I would just gain a whole lot of money. So winning the lottery has that uncertainty element, but it doesn't have loss. So in this case, there's a potential for a loss. There's something could happen at that gas station. We're uncertain about how bad and what it could be. So that's what our risk is. So when we do risk assessment, we do two things. First, we do risk analysis, which is the stuff here on the left side. And then we're going to do risk management. And so in our risk analysis, we're going to answer 3 questions. First question is, what can go wrong? The second question is, how likely is it? And the third question is, what are the consequences if it happens? And so we're going to go through this today. Once we're done answering those questions, we do the risk management piece. So we talk about the sources of risk. We talk about strategies to reduce risk. We talk about which ones of those should be priorities, because we don't have infinite resources. So how do we know, we want to spend our money on the things that are going to reduce the most risk. So this can be qualitative or quantitative. If you ever hear about this on TV, it's probably qualitative. But the quantitative forms we're going to call QRA. And the quantitative forms are going to have a whole lot of engineering behind them and not just opinions. So those 3 things I just told you about, those 3 questions are the variables. So one of our variables, J, is going to be the scenarios. So these are the things, what can go wrong. The likelihood, we're going to quantify that using probability. So we'll call our probabilities PR. And then we also have consequences. Our consequences are going to be C. So our risk equation here, if you have your pencil, you definitely want to jot this one down, because you probably don't have this in your booklet. But risk is basically, it's a probability of a scenario times the consequence of that scenario. And then we have this symbol here, which means sum. It's a summation symbol. So it means we're just going to add up our combination of probability and consequence over all of the possible scenarios that we know about. So this is kind of the crux of what risk is. It's scenarios, it's probabilities, and its consequences all together. So now let's talk about in a little more detail. We use metrics to compare risk. And so one of the metrics we're going to use is called the fatal accident rate, or the FAR. And so this is what allows us to compare risk across industries. So that way we know maybe your job is safer than my job or less safe. You know, we've all probably seen some of those TV shows on Discovery Channel involving Alaskan fishermen. Very high FAR values, not an industry that I would go into as a risk analyst. But, you know, the people who go into that kind of, I don't know, they like the excitement or something. Office workers, very low risk rates. So this metric, the FAR, is something that we can compare across industries. And what it is it's the expected number of fatalities per 100 million exposed hours. So if you think about your job in the future, you might work full-time for 50 years. So 40 hours a week, 52 weeks a year, 50 years. It's your whole career, maybe even more than your whole career. And that means that there's 1,000 of you, or your 999 of your coworkers or friends. The FAR is basically how many of those are going to die in a workplace accident of 1,000 people in their entire career. So in the US, the FAR in 2015 was just 1.8. So this gives us a basis for comparison. And this includes office workers, this includes firefighters, this includes police officers, teachers, Alaskan fishermen, everything. So this gives us, kind of our basis for comparison. So how do we calculate it? It involves that risk quantity that I just showed you. So basically, you should see that this equation right here is that same risk equation I told you there. But now we're going to multiply it by that 100 million, or when we write in scientific notation, it's 10 to the 8th. So we multiply it by that number of hours. And then we divide it by the number of workers times the number of hours in a year. So 8,760 hours in a year. And this is here, we're just going to use this today because we assume that the problem space, that there's someone working in that warehouse all the time because it makes the math easier. So we're just assuming this warehouse is always open. So that's where our FAR is. It's our risk times 100 million hours divided by the number of workers times hours. So the last thing that you're going to need to know is that we have something called an event sequence diagram. And it helps us document what our scenarios are and how we put together our probabilities. So we have something here, our circle is our initiating event. That's how an accident starts. So in this case, it's a hydrogen release. Then from A, we go over, and then B could happen. So if B happens, we say yes, and we go to the right. If B doesn't happen, we go down and we say no. And then at the end, what we're doing is we're combining the probabilities of each of those branches. So if B happens, we go across, we multiply the probability of A times the probability of B times the probability of C. And this is where Tasha gets very excited about the math. So we can come up with the probability of that scenario. On a no branch, we do 1 minus that probability. And because we know that probabilities always add up to 1. So 1 minus the probability when we go down. And these diamonds are our end states. So they're the things that we're worried about that we either know are okay or that we're trying to prevent. So part of my job is building these event sequence diagrams. And part of that is part of this whole risk assessment process. So the first thing we want to do is set our analysis goals. So that kind of relates to figuring out what our FAR needs to be or why we're doing this. Then we describe the system and the hazards. Then we describe what causes those accidents and what the consequences are. And then we're going to communicate about the results. So this is something that I would spend about a year on. But I've set up this kind of same 5-step process for you so you have all of the right pieces. So now let's talk about the problem. So hydrogen forklifts, they can be used instead of battery or propane forklifts. Are they safe enough to put inside of a warehouse? Let's find out. So at this point, I think you probably want to grab your packet because these 6 questions that are on the screen are the same 6 questions that you're going to be asked in your packet. So I'm not going to read them off. You don't need to write this down. You're going to have to answer these 6 questions. So I set up the goals of your analysis. That was step 1. Step 2 is to tell you what this system is like. So this is a warehouse. It's a 100,000 cubic meter warehouse. It has some forklifts in it that are used to lift things. And we have a fuel dispenser that's going to be used to fuel up those forklifts. So in this warehouse, let's assume that there's 50 people in there working at any given time. So they're there, 50 different people there all the time, 8,760 hours a year. Someone is very nice and works on every holiday so that we're still getting our food. So now, what are our hazards? What can go wrong? Remember, I told you the first question was what can go wrong? Well, when you have hydrogen, just like gasoline, it is flammable. And that's our big scenario that we're worried about. We don't want to have a fire. So for a fire to happen, we need 3 things. We need a fuel, we need oxygen, and we need heat, or something that will set it on fire. So that's called our fire triangle. Anything needs to have those 3 things to catch on fire. When you have fire, when something catches on fire, there are some side effects. So you can get heat, you get the flames, you get gases. So of course a flame is hot, but it's also full of really nasty toxic gases. And you can also get high pressure from basically pressure generated from exothermic reactions. So we'll call that overpressure. So what you need to know about fire today is that hydrogen gas stations can cause 2 different kinds of fire. So think one of them is like a jet flame. So if you're in chemistry class, you have your Bunsen burner, you get that nice little tube of flame. We'll call that a jet flame. And then the other one could be like an explosion. So imagine that we put too much air inside a balloon and we just keep blowing it up and keep blowing it up until the balloon pops. Well, if that was colorful, if that wasn't clear air, but it was a colorful gas, you might see the explosion happening. So imagine just a balloon full of fire when you add too much to it. So step 3, here's our model, our event sequence diagram that I told you. So our first thing is that we have a probability of a hydrogen release. That's our initiating event. But remember, this is not just a picture, it's also an equation, but you're going to have to put together kind of the pieces of the equation. So if hydrogen is released from our gas pump, we have some interlocks. We know that we have a leak detection and isolation system. So if something is leaking, there's a system that's going to shut it down. But the system's not perfect. But if the system works perfectly, great, we go right here and we have no ignition. It's green because we're still having a good day. You know, we can't get gas, but that's okay. Everyone's happy, no fire. Now let's have a bad day. If the leak detection system doesn't work, we could have an immediate ignition. If we have immediate ignition, that means the hydrogen gas pump catches on fire right away. We go across our ES and we get a jet fire. So remember, that's kind of like our Bunsen burner. So we have a Bunsen burner like fire. If it doesn't catch on fire right away, but it catches on fire later, it's called delayed ignition. We had time for it to accumulate, just like our balloon. If it accumulates, we have a really bad day. That's really bad. Jet fire is not a good day. It's not nearly as bad as an explosion. So worst day is that our gas accumulated inside. If we're lucky, it might not even catch on fire. And in that case, the hydrogen goes away. So we have no ignition. So I've answered everything about what can go wrong. You know, everything you need to know for that first we've answered the first risk question. Step 4 is that we have to figure out what our consequences are. So those green end states, no ignition, everyone's safe, no fatalities. The yellow and the red, those are our bad consequences. Those are the things we really want to avoid because that's how we injure or kill our workers. So a jet fire, we assume that that's gonna kill one person. So we're gonna have one fatality. An explosion is gonna collapse the building and it's gonna kill half the workers in the building. And we want to avoid both of those, of course, but again, we have to figure out probability together with those consequences. So here you have the info you need for your consequences. And on your worksheet, you're going to have some of the probability info you need. And then the last thing we're going to do is we're going to compare the calculated FAR to the Bureau of Labor Statistics. So what's really cool is the Bureau of Labor Statistics calculates these FARs for about 10,000 different jobs. Every job you could imagine is on that list. So I already told you the US workforce total is 1.8. Construction workers, it's a lot bigger, it's 5.9. People that work on industrial machinery, it's up to 10. So anyone working on, maintaining forklifts has a really high FAR. And then you have these two categories down here at the bottom. Industrial truck and tractor operators. This is our category for forklift drivers. So it's 3.0 for forklift drivers. This is actually the number for people working in warehouses that are not driving forklifts. It's a tiny bit higher. So these are the rows that we're looking at and that we want to consider in coming up with our result. And this chart is in your problem packet. So now with that, that finishes out the problem. You have everything you need for solving this problem. So I'll go ahead and turn it over to our hosts to explain, send you out to the breakout room and go ahead and work through this problem. Or I could take questions first. It's sorry.
You might want to just, you might want to just see if anyone has any questions before we send everybody off to the breakout room. That might be helpful. So there's someone that's their hand raised here. So let me see.
A quick question. What or with the FAR, can it fluctuate? Like for example, like with like hospital workers in like the past year and stuff like that, would it would still go up, or if
Yeah, that's a great question. Yes. Oh, did we just lose her or is she just muted?
I think she just muted. Yeah.
Okay. Yeah, that's a fantastic question. Yes, it changes year by year, and especially this year, or if we look at 2020, the 2020 data is not out yet, but absolutely it's going to be higher this year. So when we look at this in real problems, we're usually looking at plots of how it evolves over years. And we also have to consider, was there something, special that happened that year, or something very weird that happened that year? So yes, the FAR will definitely, I would anticipate that it will definitely go up this year just because of what's happened with the pandemic. But it does take a couple of years usually for the data to come through because you have to do a lot of validation on that data. And I don't think we have those numbers yet.
Okay. Well, if there's no other additional questions, I know that some of the GEM girls will be coming into the breakout rooms. We have 7 breakout rooms today to help and assist you in figuring out your solving for the problem. So hopefully they will get to you. If not, just ring us and we'll try and visit and assign someone to you. All right. So you have 15 minutes and then we'll close the rooms and we'll come back here and discuss. Here we go. I think, Michaela, you have to hit join.
Yep, I got the control.
Do we want to give him more time to read, or should we just pop in?
I think we could just pop in. I'll go to I'll go to room 6.
Okay, I'll go to 4.
Mhm.
Okay, I have it typed up too, so
Okay.
so I won't have to iPad it quite as much.
Yeah. Everyone's coming back. I think everyone is back. Well, we know that was a tough problem. So hopefully you kind of came together in your groups, but Dr. Groth here will help walk us through what that assessment should be.
Okay, so yeah, we'll go through this solution together, but what I'm going to ask is anybody who was able to finish part 4, the calculate the total FAR, type in the chat, just one person per breakout room, please. Type into the chat what your FAR number was for your group, if you were able to get one. And if you weren't, don't worry, I think we'll go over it together. Okay, great. Breakout room 4, I have 0.09. One of the breakout rooms, you got 4.86. Okay, we'll wait for a few more numbers to come in. Let me share my screen as I do. I know this is a pretty tough problem. And the numbers were kind of deceptively simple, but it's a little bit of a tough thing to do. And these are real numbers. So these are the real numbers from a real problem. So I started annotating this way because it's going to be hard to type it. But for part 1, so remember you had this picture that you were given. And remember our first bubble was filled in. It was 0.01. So one of the things that we learned in the problem statement was that leak detection was effective 90% of the time. So remember when we read yes across, so if we have a hydrogen release yes, 0.01, the leak detection probability is 0.9. So to fill in this other blank, we have to get the probability of the other thing happening. So if we know that 90% of my balls are red, I have to do 1 minus 90%. So 1 minus 0.9, which is 0.1 to get on my bottom line there. So what I did was I started in this picture that you're seeing as I wrote all my numbers across the lines. And then to get the fill in the blank, I have to do 1 minus that. So for the next line, it's 1 minus 0.053. So that was 0.947. And then we do the same thing to get that last number, 0.973. And I wrote those numbers here in case you can't read my handwriting with my mouse, so you know what the numbers are. So now what I'm going to do is I'm going to change colors so you can see what I do next. So number one, I just did, that's in red. Actually, I'll check that off in red. Probably shouldn't use red for that one because that's actually, okay. So now let's do our yellow scenario. So what I want to do to get this probability of this yellow scenario, I follow my yellow path. I had a hydrogen release, my detector didn't work. Yes, I got immediate ignition. Follow my yellow path. So what we figured out in Rowan's room was that when we follow this path, we're basically picking up the numbers as we go. So that yellow path, I'm going to pick up that 0.01. I'm going to pick up the 0.1, and I'm going to pick up the 0.5053. So when I multiply those three numbers together, you should get a really, really, really small number. And if you're familiar with scientific notation, it's going to be 5.3 times 10 to the negative 5. And if you're not familiar with scientific notation, you probably got 0.00053. Again, forgive the handwriting. So those are the same number. So if you were able to get for number 2, that's 0.0005053. There's 4 leading zeros there after the decimal. That's the probability of having this jet fire scenario at this warehouse in a year. It's really tiny. I know it's a very tiny number, but the good news is it's a very tiny number, which means we probably should be feeling okay about this system. So that's that color. Now I'm going to do purple. So that's 2. Now number 3 is purple. So same thing. I go through my tree. I go down here. I didn't immediately ignite. I go here. So I got my 0.01. I have my 0.1. I have my 0.947. And I have my 0.027. So when you multiply that all out, you should get 2.56 times 10 to the negative 5. So that's our number for there. And in case you were curious, I put in the numbers for all the scenarios. So what you'll see if I underline all of the good scenarios in green, we know that things, times 10 to the minus 3, that's a much bigger number than times 10 to the minus 5. So if you did the math on this, give me 1 second. I actually did the math behind the Zoom. So let me pull up my exact numbers. Okay, now back up to the Zoom. So if you did the math on these, just to see, how your scenarios were ending, 90% of the time, even if we have a release, 90% of the time, the leak detection is shutting it down. And 9.2% of the time, we're still having no ignition. So we're at 99% of the time, 99.2% of the time, even if there is a leak, that there's no fire. And the rest of it is these other 2 scenarios. So that's where numbers 1, 2, and 3 came from. We're just kind of multiplying across that tree. And then number 4 is where we bring it all together. So there was a couple of things you needed. So we know what I wrote the FAR formula here again. And so we knew the 10 to the 8th is going to stay the same. We knew our 8760. And we knew one of the things you were given was that there were 50 workers in the warehouse. So we have those 3 pieces we needed. The last thing we needed was we had to come up with the probability of the scenario times the consequences of the scenario. So remember, for the jet fire, we said that the jet fire caused 1 fatality. So we multiply that 1 fatality times the probability from that jet fire scenario. So it's 1 person times 5.3, 10 to the minus 5. And then our other scenario that causes consequences was the explosion. So we know that that's less likely. We know what its probability was, and we know that it killed half the people, and half of 50 is 25. So when we put all of that together in our calculation, we would get 0.158. So that's how we do the math part of it. But I kind of expected that maybe that math would be a little bit hard and most people might not get the math perfect. So that's why I wrote problem 5 the way I did. So let's go to our final answer, and then I want to have a discussion about what that answer means. So we have 1.158. So you'll remember that. So if you solved part 4 correctly, you got 0.158. And there's a couple of ways you could have gotten a slightly different answers by making mistakes, but that wasn't the point of this. So I wanted us to have a conversation about, is it safe enough? So my value, so this was a real analysis, like I mentioned. In our real analysis, the number was very close to this. And what we were comparing it to was essentially that 3.0 or that 3.1. And so what you'll find out is this number is a whole lot lower than the risk that people driving forklifts are already taking. So in doing this analysis, we determined that yes, it was safe enough to have the gas pump inside the warehouse because it was, really tiny contribution to risk because we had this ability to look at it. But what I'm interested in hearing is what the other groups thought about that. So if, let's pretend your number was right. So I know that someone got a number of 0.09. So if you got 0.09, did you think that that was safe enough? Did your group have a discussion on whether that was safe enough? And then if I think someone else got 4.9. So if the number was 4.9, do you think it was safe enough then? So let's have that discussion, because that's the discussion we really have once we get these numbers. So let's have that real discussion and tell me what you think based on, we'll just pretend your number was right and tell me what your group's number was and what you thought.
So ours was wrong, but 4.86 would definitely not be safe enough because it's like way above the 3.0 number.
Yeah, great, absolutely. If I saw 4.8, I would definitely think we need to figure out how we reduce that risk because it's way too high. I think Ayusha's hand is up.
Yes, so we got 0.9 and we thought it was safe because the number is very low. It's like the lowest among all of these.
Yeah, absolutely. Yeah, with the number that you all got, that's probably what I would conclude too, is that it was, pretty safe compared to everything else that they're doing at work that day. So then the last thing we would do, does anyone else have a number that they want to volunteer before I kind of go back to what the last part of the question? So the last part of the question then is, what else should we do about it? So now we know that we want to reduce risk. So we always, of course, want to think about how we make it a little more safe. And so as engineers, one of the things we do is we use this model and we'll do more mathematical analysis with it, kind of like I showed you. Oh, 90% of my scenarios are unignited safe. We do more analysis and we figure out what do we do to reduce that risk. So if our number was 4.9, that's definitely unacceptable. So what are some things we could do to try to get that number down? And we're not doing this to play math tricks. We're trying to say, let's redesign this system to make it safer. So what are some things that we could do with everything you know now about this system? What's one option that we could do to help make this safer?
Keep it in like an isolated area, because like it said that like even though we prohibit smoking and lighters, static electricity can still like cause it, even though it's like a very small chance it could still possibly happen.
Fantastic. Autumn, you should just come to grad school, come over to the University of Maryland, you're always on it. So that was actually one of the things we figured out, was that we could isolate these things. So put them in a room where there was fewer people, and also what's called electrical classification, which basically restricts what else can be near it that could cause a spark. So remembering our fire triangle, we need fuel, oxygen, and spark. So basically Autumn just hit on two things. One was get rid of the sparks, and the other was kind of reduce the number of people that are around it. And so both of those will bring your numbers down. So the sparks are going to bring down your ignition probability, and reducing changing the location so it's closer to a few people, that's going to bring down. So we're going to bring down this number. We control more sparks, and we're going to bring down these numbers if we limit how many people are near it. So one thing we did was actually someone using the gas pump doesn't stand right next to it. They have to get away from it so that they're far enough away if something goes wrong. So that was actually a solution we came up with in doing this problem. Looks like Avery has her hand up. Avery, tell us what you think.
I think if it was that high, maybe we could try to, like, you know how there's like the sensors that detect the fuel, if like you double check those and make sure they work like every time you get in it, so you're not like getting into something dangerous.
Fantastic. That is also something that is required in this code. So great. Yeah, you're coming up with great solutions. I think I saw Ayusha's hand up next.
So like in school we have drills for fire. We could have like a drill just in case for emergency.
Yes, absolutely, because that gets your people away from your fire. So one of the things we know is that you don't actually, with these fires, it's not going to hurt you like immediately. You actually have to be in the fire for a little bit. So if you can get people trained to get out of the fire, then you're going to have both of these numbers go down. So great. Amaryllis.
I have a question about how the fire drill thing would work, because in school they like when we do fire drills they make us go in lines and like all together, but I don't think that's what would happen if there was a fire in school. We would not go in lines. Everybody would be panicking, obviously, unless if it was small, then that makes sense, but if it was like a huge fire, then you wouldn't go in lines. Everybody would be scared. So how would that work with what we were talking about?
That's a great question. So one of the reasons that we do these practices like drills is so that we can try to do it the best we can when it's not actually on fire. So that's ideal behavior. We always want to try to be, when we practice things, we get better at them. That doesn't mean we get perfect at them. So if you saw a really giant fire, you would probably want to get out as quickly as you could. But with a lot of these fires, they start small before they get big. So you actually have time before the fire gets big. And so what happens in fires is that people kind of do some weird things. If they see a small fire, they think, oh, that's not a big deal. Let me go get my friend. Let me go see if Avery next door is here. And they stay in the building for too long. So what you want to do is never check on your friend unless your friend is like someone who can't walk or someone who can't hear the alarm or something. But you should always get out of the building when you hear the fire alarm going off and do it as quickly and safely as you can, because that's why. So people, when they don't practice it, they check on their friend, they go pick up something from their locker first. They do things like that because they're like, oh, this fire is small. Don't wait for the fire to get big. Get out of the fire.
Sorry, I have one more follow-up question. So like, how are you talking about like, oh, like don't wait for the fire to like get bigger and stuff? What would happen if like nobody knew that there was a fire and it already became huge and then the alarm went off, like it touches the alarm? What would happen then? Like, would you still have to like follow what the teachers are saying like in line, or like would you like just run or like leave to the closest exit faster than that?
Well, hopefully your teacher is going to take you out the closest exit as fast as possible. The other thing you want to avoid is like if everyone starts running whichever way they want and you only have a doorway that's one person wide, you don't want to get all stuck behind the doorway. So if I would follow, if you don't see the fire, I would say follow your teacher's instructions. If you start seeing the fire and for some reason your teacher is not very quickly getting you out of the room, I would look for a window and start getting, going that way. But there's a lot of things that can make fires bigger. And so usually it really depends on what the building looks like, what the exits look like. So that's why they come up with specific plans for your specific school. And in these things, actually, we come up with specific plans for specific warehouses based on where the doors are, how many people are in them. So the best guidance is always to get out as quickly and safely as you can. But without knowing anything about like what your school looks like, your teacher really would be the one who knows more about it. But if your teacher is, you know, I don't know, like smoke got to your teacher and they're not breathing anymore, get out of the fire as quickly and safely as you can.
Yeah, and so like, so you know how you were talking about like, oh, like make it safer, like so like the explosion won't harm as many people, or like if there was one to happen possibly, would you add like people were saying in the chat like making like big exits near the near the thing, and so like people could escape faster and therefore less people would die and or get hurt.
Yeah, that's a fantastic idea. Bigger exit doors is always a really good idea because you can get more people out. So yeah, great suggestions. Other suggestions from other rooms? I think I saw Alicia. I might be volunteering you though, but you were nodding like you had a suggestion earlier.
Oh yeah, I just like I put this in the chat, but like placing the fuel stations like close to an exit so that if something like happens near it, like you can just like leave quickly and not go through the entire like warehouse.
Yeah, fantastic. Yeah, putting it near exits. Amen?
Oh man, you could also make like bigger signs that indicate where the fire exits are. So if anyone were to like run anywhere, they could see, oh, there's the fire exit, so they could run out.
Exactly. Yeah, signs and big exits and knowing where they are these are all fantastic suggestions.
Or like you know how like the alarm goes off when there's a fire, like in school and stuff, like maybe like you guys would like set like a voice thing, like so when anything close to smoke or like overly heated in the warehouse, you know, like it would make a sound and then the sound would give instructions to people who like can't stop and read a sign to, you know, like which way to go or something.
Yeah. Yeah, we have lots of great suggestions. And these are like what we're really thinking about when we're doing engineering is which of these do we want to do? What's the most effective? So my challenge for you is the next time you're at a gas station, one other thing you're going to see at a gas station is there's a big red button that says emergency shut off. So one of the ways we detect leaks is of course through sensors like your smoke alarm, it detects smoke. But there's also you. So if you know the gasoline is leaking at a gas station, there's a big red button at just about every gas station that's called emergency shut off. Obviously you don't push it unless it's a true emergency because otherwise you'd be hurting people. But take a look for it the next time you're at the gas station with your parents. Another thing we do is we have that shut off. So that way we have kind of a second leak detector, which is the human who's filling it. And at any time, if they notice something that starts to go wrong, they can push that button to turn it off. In a warehouse, we would all, of course, be trained on this. At the real gas station, it's usually just the gas station attendant. So that person that's there who also sells you sodas, that button's usually there. If that person sees something like a fire, they run out and push that button too. And that's another way that we make our gas station safer. So I know we're right on time. So, I see a question from Alicia.
Yeah, like at like a hydrogen like fuel station, would spacing each of the like fuel dispensers out be like a good idea?
Yes, that's another thing. So that's actually, we call that a separation distance. And one of the regulations that we've written using this analysis was how far those distances needed to be, both between the gas pumps, but also between like the gas pump and the convenience store or the gas pump and a public road. And so that was a really big part of the use of this real analysis was determining what the separation distances between things needed to be so that if we had a fire, the people could get out of it, but also it wouldn't propagate to other gas stations, to your car and to other things. So when you start looking at gas stations, you'll start seeing like, oh, there's more space between the pumps and the front door than between each of the pumps. And so, yeah, making distance between things makes it less likely that the fires will expand beyond a single pump. So that was kind of it for the problem. Does anyone have any other questions? Just general stuff. What's it like being a woman in engineering? Should I go to college? Any of those things? I have plenty of time, and I was a girl in middle and high school one time, so I'd be very happy to answer any of your questions too about just life as a woman in engineering.